Welcome to Section 7C. This is where we're going to talk a little bit about gambling, but we're going to start out with the law of large numbers. Before we move into the definition of the law of large numbers, we need to define that the probability of event A is stated as P of A, or probability of A, and the results of the repeated trials are independent. So the law of large numbers states, if the process is repeated through many trials, the proportion of the trials in which the event A occurs will be close to the probability P of A. The larger number of trials, the closer the proportion should be to the probability of A. Now, I don't really like that definition, so what I say is I think of it as being the empirical probability. Now remember, empirical is what you're observing and watching and happening. That the empirical probability is getting closer and closer and closer to the theoretical probability, which we know is just in a perfect world, what would it be? So we know exactly how many sides are on the dice and what it should end up being with the theoretical probability. I like these two graphs because it shows a little bit of what the law of large numbers looks like. Now, at the beginning, we're going to get lots of different percentages of flipping, let's say, a coin. Heads and tails, it's going to flip back and forth pretty dramatically, but once we start adding more and more trials, it's going to end up getting closer and closer and closer. In this case, it says 0 because it's talking about the difference between heads and tails, but if we wanted to look at it as being 50% heads and 50% tails, I like that better. And notice our number of trials goes from 200, 400, 600, 800 to 1,000, and it's getting closer and closer. If your coin is fair, it should be getting closer and closer to the 50%. Over here, here's another one also showing it's going to bounce around a little bit and it's going to get closer and closer. It might go above, it might go below, it might stay below and just get closer from below. Either way, that's how I like to look at it. So we're going to move on to applying the law of large numbers with our first example in roulette. Roulette is a wheel. It has 38 numbers, 18 black, 18 red, and 2 green. And the green numbers are 0 and 0, 0, which is very important. We'll come to that later when we talk about the house edge. So if I wanted to just find the probability of getting a red, well, I have 18 red out of 36, and I get the probability of 0.474. So if I spin a roulette wheel 100,000 times, how many times should I expect to get the number red? Well, I take my probability of 0.474 times it by 10 or 100,000, and I should expect to get about 47,400, or 47.4% of the time. Now that's the theoretical. And the more and more I spin, the closer it will end up being this theoretical 47.4%. Roman numeral 2, expected value. We're going to first talk about an insurance company. Let's suppose that they have a 1 in 500 chance of a claim holder or a policy holder making a $100,000 claim. And let's suppose that the policies are about $250 each. So if they sell 100 policies, 100 times $250 gives us $25,000. Which, if one person made a claim out of these 100 policies, it would put them in the hole with just one claim. An insurance company will only be successful if they sell a very large number of policies. We're going to go on the conservative side and say that they sell about 1 million policies. I know it doesn't sound like 1 million is going to be conservative, but believe me, in an insurance company, that's going to be pretty conservative. So, how many $100,000 claims should we expect if we did sell 1 million policies? So we know that there is a 1 in 500 chance. So 1 out of 500 people for these million will give us 1 million times 1 out of 500, which gives us 2,000 claims. So these 2,000 claims, how much does the insurance company need to pay out if it has 2,000 claims? 2,000 claims at $100,000 per claim. 2,000 times 100,000 ends up being $200 million, a substantial increase from what we talked about with only one claim. So will that put them in the hole? Let's look at their profit. If we sell 1 million policies at $250 each, that's $250 million towards the insurance company. So 250 million minus the amount from the claims still ends up giving them a $50 million profit. That moves us to our formula for expected value. Expected value is calculated by finding the value of event 1 timesing by the probability of that event. And then I add the value of event 2, times it by the probability of event 2. Oops, typo. And then I keep going, add it to the value of event 3 times the probability of event 3, as many events as you have. Let's go ahead and use our formula on our insurance example just to kind of show how it works. So the expected value of each insurance of the insurance policy to the insurance company. The expected value, so I need to figure out what is the value of event 1. Well, event 1 would be the claim or the policyholder buying the policy. So if I'm the insurance company, that $250 is coming into my bank account, so it's a positive $250. If I was talking about this in a different perspective, instead of the value of it to the insurance company, but the value to the policyholder, if I bought that policy, that $250 would be negative because I'm paying, it's money coming out of my pocket. And so that would be negative. It's very important on these expected values to make sure that you have the value of that event. So put yourself in the position of either the insurance company or the policyholder, whichever one, so that you know you're getting the positive and negatives correct. But this $250 is coming into the pocket of the insurance company. The probability of this happening is 1 because the customer actually bought the policy, so it is definitely coming in. That is a 100% guarantee, or they aren't going to be a policyholder. So the probability is 1. Now the second event is that this policyholder actually makes a claim. Now if they're making a claim, this is money coming out of the policyholder or out of the insurance company to the policyholder. And so this value is negative because it's a payout from the insurance. The probability of that happening, we talked about earlier, is 1 in 500 or 1 out of 500. So let's calculate it out. $250 towards me as the insurance company times by, it's a sure event because they buy the policy. Now the claim would be money away from me of $100,000, and the probability of that occurring is 1 out of 500. Plug that in your calculator or Excel, and you end up getting with $50. The expected value of every single policy is $50 in profit for the insurance policy, or the insurance company, for every single policy sold. But this is the law of large numbers. And that makes sense. If we had $50 for every policy sold and we sold 1 million, that still ends up being the exact same thing as what we found earlier, is a $50 million profit for the law of large numbers. It has to make sure that it hits a large enough number for it to take an effect. Let's do B. Let's find the expected value of a lottery ticket. You walk into a convenience store, you buy a lottery ticket, it costs $1. The probability of winning the first prize is 1 in 5, and you win $1 for a free ticket. The next prize is winning $5, and the probability of that occurring is 1 in 100. The probability for the third prize is winning $1,000, and it is 1 out of 100,000. The probability of winning $1 million, the jackpot, is 1 in 10 million. So what's the expected value of your ticket? Now, a lot of you are thinking, well, the expected value is that you bought your ticket and you're probably not going to win, so it's minus $1. But remember, you do have a very small chance of winning something. So, what's the expected value? A little different than just what actually occurs. So, the expected value, the value of event 1. So, event 1, you walked into the store, you bought the ticket, and the ticket cost you $1. So it was money, $1 away from your pocketbook. The probability of that event happening, well, you bought it, so the probability of that event is 1. It's 100% certain because you paid your dollar to the cashier. Okay, let's find the value of event 2. This is winning your first prize, so the value of that is the $1 in your free ticket. And the probability of that occurring would be 1 out of 5. Then I need to add the value of the third event, which would be winning the second prize, and timesing that by the third or the second probability, and the third event and the fourth event, and so on. So the first one, we have -1 times 1, which we have $1 away from you, 100% being the probability. Now here we have $1 in a free ticket and the probability is 1 out of 5. Then we add it to the next one, which was a $5 prize, and the probability is 1 out of 100. The next event is winning $1,000, and the probability of that occurring is 1 in 100,000. The next one is winning $1 million, the jackpot, and the probability of it happening is 1 over 10 million. Plugging that into your calculator, or once you have it typed out, you can just copy and paste that into Excel. But remember, Excel needs to have those multiplication signs in between. Your calculator, if you have a scientific one, won't, or a graphing calculator, you don't have to. But, and I'm going to take out that $sign. But in Excel, there's so many different functions that it needs to be told. Oops, I missed one. Oh, it doesn't like commas, so we'll have to take those out too. So let's just assume we took out all the commas. No, we'll take them out. There's only a few. All right, there we go. -60.64. There we go. Your expected value as a ticket buyer, you should expect a -64 cents at every single ticket you buy, just by picking up that ticket and paying your dollar. All right. The next one is the art auction. A bid of $50,000. So you're at an auction and a bid of $50,000 for a painting, and you have a probability of 1/2 of reselling this painting. You have a specific client in mind of $70,000. There's also another probability, a 1/4 probability, that you could sell the same painting to a different client for $80,000. What's the expected value of your bid of $50,000? Okay, so let's find every single event we need to work with. The first event is bidding and winning the painting for $50,000. The next is reselling it for $70,000, and we have the probability here. The third event is selling it to a different client for this amount, and we have its probability. So the event 1, you buy this painting with your bid of $50,000. Now that's money away from you. And if this actually happens, the value of this bid, or the probability that you're buying it, is 100% because you're going to buy that painting. The next is event 2, selling it to your first buyer or client, was $70,000, and there's a 50% probability, or 1/2 probability, that that will actually occur. Then the value of, or the third event is selling it to the second client, and the value of it would be getting a payback of $80,000, and the probability, we were told, is 1 out of 4. Plugging that into your calculator or Excel gives us an expected value of $5,000. So if I were to go ahead and make this bid, I should expect about $5,000 as my expected value. Now, the law of large numbers says that if I have the same probability of reselling these kind of paintings, the more I buy, if I buy many, many more with the same probability, I should expect about $5,000 per painting. Now, will I always get 5,000? No. Sometimes I might end up getting less and having to take a cut, or there will be times where I'll end up spending or selling it for even more than what I was planning. And but it all ends up balancing out, just like we saw in our law of large numbers graph. It'll kind of go back and forth, and the more and more and more I buy um, of these paintings, if I have the same probability, I should expect about $5,000 per painting. But you do always have the risk versus reward, and we talked about that in the finance section. You have to balance it. Do you really have that probability of reselling to these different clients? That's something that you would have to weigh with the risk and the reward. We're going to move on to Roman numeral 3, which kind of is nice because we already talked about the expected value of the lottery ticket and how it's really not worth it. You just expect to throw the money away. The gambler's fallacy. There is a mistaken belief that a streak of bad luck must be followed by a streak of good luck. And it kind of makes sense. A lot of people look at the law of large numbers thinking that the empirical is going to get closer and closer and closer to the theoretical, and therefore it has to balance out. But not necessarily. In fact, let's go up to this one. This graph here is showing that the law of large numbers is at work. I'm getting closer to the theoretical, this line here. However, I'm coming at it from below, which means I'm still losing. Now this one happens to dip up, but it doesn't have to. It can stay below and just get closer and closer and closer, but never go above it. So that's the gambler's fallacy. Another part of the gambler's fallacy that needs to be remembered is that each event in these gambling arenas or events are completely independent. If I toss a coin, the first toss does not affect the second toss. If I roll a dice, the first roll does not affect the second roll. And even though it is getting closer to the theoretical probability, it doesn't necessarily mean that you're winning. And we talked a bit about that, about Chevalier, I believe was his name. All right, let's move on to our first example in a coin toss game. By the way, I have a funny video from BYU Studio C. They have kind of a skit that you can go look at that kind of shows what you would do on this one. So this coin toss game is that you win $1 on heads and lose $1 on tails. After 100 tosses, let's say you get 45 heads and 55 tails, which means that you are in the hole $10 because between here and here there's 10 tails more than heads, and so you paid out $10 more. Let's say that you continue to toss this coin 1,000 times, and then you get 480 heads and 520 tails. Is this kind of going in agreement with the law of large numbers? And do we get any money back? So the first thing we talk about in the first game, you have 45 heads out of 100, which is 45% heads. It is close to 50%, so we're not going to assume that the coin isn't fair. And then in the second game, we have 480 heads out of 1,000, which gives us 48% heads, which means I am really getting closer to the theoretical. I'm getting closer to that 50%. It's going from 45%, and I do a bunch more, and I get up to 48%. However, I'm still in the hole because I'm betting on heads and it's 520 tails. So in between these, I have 40, a difference of 40, which means I'm $40 behind here, and the original $10 behind here. I'm now in the whole $50 after the 1,000 times. Part of the gambler's fallacy is just this. I am getting closer to the 50%, but it doesn't mean I'm winning. Let's move on to the next one. This next example is called craps. This is a rolling dice game. A hot hand in craps means that you're winning 10 consecutive bets in a row. And should you then increase your bet now that you're on a hot streak? Well, let's assume that it's a 0.486 probability of the best odds on a single play. So we're going to consider just the chances of winning 10 consecutive wins in a row. So we have 0.486 for the probability. 10 wins in a row, raise that to a 10, gives us the probability of what you just have of this hot hand is 0.0735, or 7 out of 10,000. So yeah, it's pretty rare that you've actually got this hot hand. But the next roll, your probability is still the exact same, 0.486. It doesn't change because these are independent events. Let's move on to the next thing, called the house edge. I like to think of this as the casinos are the ones making the money. All you have to do is look at pictures of Vegas. I lived there for a while and I know they are definitely making the money. The house edge is the expected earnings of the patron, or the expected earnings of the patrons is totally negative. The money expected to earn per dollar is the house edge. Every dollar that is bet within the casino is expecting to earn money towards them. And they do, because of the law of large numbers. Now let's move on to what's called the house edge in roulette. And we're going to do just roulette because it's really nice and simple. We have all of the numbers, and I liked this picture a little better than the first one because it shows you the green 0 and the double 0. That's the house edge. Those two little numbers is all it really takes. All right, if we wanted to bet on a color, red or black, the payout is a 1-to-1 bet. That means if I bet $1, then I win $1, and of course you get your $1 back that you bet previously. The probability of red occurring, there are 18 reds out of 38 total possibilities. The probability of not getting a red, now remember, there's 18 reds, 18 blacks, and 2 greens. So the probability of not getting a red would be the 18 blacks plus the 2 greens, which is 20 out of 38. Betting on a single number is a payout of 35-to-1. That means if I bet $1, I'm going to get $35, and of course the $1 that I bet in the first place. Let's find the house edge, or the expected value, for the casino when a patron bets on red. So that's a $1 bet. So we look at every single event. The first event is that the patron bets $1. So this $1 is coming to the casino. It's a positive number. If you want to put it in there, you could put a plus sign, noting that this is money coming to the casino because the patron is betting on that. Now the probability of that coming to the casino, if this person is betting on red, the probability of not red, meaning that that's when the casino gets the payout, is 20 out of 38. That's the probability. The next event is that you have to pay the patron $1. Now notice it doesn't say that I'm paying them $2, because when they bet their dollar, that dollar is just kind of sitting there in limbo. That's not yours nor theirs anymore if you're the casino, and then you just give that dollar back to them and you pay them one of your dollars as the casino. The probability of the patron winning, so if they bet on red, the probability is 18 out of 38. So I have 18 out of 38. We can simplify that up just a little bit by doing getting rid of all of the words in here, and I have $1 coming to the casino with a probability of 20 out of 38. Add it to a $1 payout, and the probability of that occurring is 18 out of 38. Plugging that into your calculator is 0.053, or 5 cents. The casino is expecting to make 5 cents on every $1 bet on a color. It doesn't sound like a lot, right? 5 cents, right? But remember, the law of large numbers. These casinos don't just have one person walking in and making a single bet. They have thousands of people that come through on a single weekend. So let's say in one weekend, the casino will see $1 million in bets on red alone on the roulette tables. So what are they expecting on this one weekend with the $1 million bets? Well, they expect to make a little more than 5 cents for every single $1 bet. So 0.053 times it by 1 million, they expect $53,000 just in red bets alone in the casino. And because the probabilities are the exact same for black, we can assume they can expect to win $53,000 in that weekend just on black as well. So 106,000 every weekend just on betting on a color. They're the ones making the money. Let's look at the house edge when betting on just a number, which has a bigger payout for the patron, which means as the casino, it has a bigger payout. However, the probability of it occurring isn't very much. I'm going to scoot back up here just a little bit so that we can see the roulette table. So let's talk about each event. The value of event 1. So the patron puts a bet, a $1 bet on a number. They pick their birthday, and the value of event 1 is that $1 is coming towards you as the casino because they put that money down as a bet on a single number. The probability of you as the casino getting that money, let's see, the probability, do you remember there are 18 reds, 18 blacks, and one green, or one double green, 1 0, and a double 0, so 2 greens. That all adds up to 38. So if you bet on one number, that gives us 37 out of 38 other numbers not occurring, so that money would go to the casino. The value of event 2 is that the casino is paying out $35 if that patron wins. But the probability of that happening, there's only 1 out of 38 for that number to actually occur. So let's plug it into our calculator. $1 towards the casino. The probability of it coming towards the casino is 37 out of 38. Add it to the probability of event 1, which would be the value of event 1, negative $35. They're paying that out. The probability of them having to pay that out is only 1 out of 38 because you're betting on one single number out of all 38. Gives us 5 cents, a little over 5 cents per dollar. Same house edge. Which means, again, if the patrons bet about $1 million in one single weekend on just a number alone, and it doesn't matter any of the numbers, they can expect to win yet another $53,000 on the roulette tables with just that kind of bet. Interesting, isn't it? So in a single weekend, 53,000 on red, 53,000 on black, 53,000 on the numbers alone, and this is just with the roulette tables. They are definitely the ones making the money. We've been counseled by the Prophet, and there are reasons we have been counseled. Not only is this an addictive habit and very dangerous path to go down, but mathematically it doesn't work out either. All right, I hope you join me with our next section, which will be the last of the semester. Good luck.